Okay, so hello everybody. Next speaker is Alexander Frei from Copenhagen and in Waterloo soon. And he will talk about the relative Cuntz-Pimsner algebras, classification and applications.
Thanks. So first of all, yeah, so as already mentioned, so I'm not yet there in University of Waterloo. So I did my PhD with Søren Eilers, he was also here, hi Søren. In Copenhagen. And yeah, so that's why there's a star, just wanted to make it clear that, okay, I haven't started there yet. And so also thanks for organizing this really nice workshop conference. I think, yeah, so we can maybe thank later. So, okay. So I'm going to talk about relative Cuntz-Pimsner algebra. More precisely, I will talk about systematic classification of such. And so this goes along the way that basically pieces can be found together in literature of their classification. However, in a I don't want to say ad hoc way, but I mean it's at least not in a very not in a very systematic way. And so it's rather how to say boil down to the faithful case and things like this, and then you can match things together if you know how to. And so this is what I did. So basically I realized that okay, that the main results are already available, and you just have to paste them together and you get a very clean systematic classification of that. And with this, so this also meanwhile also gives another another way to view relative Cuntz-Pimsner algebras. And this view, this perspective or this classification gives a very neat description, which allows in a couple of applications also to understand them, to treat them in a systematic way. And so let me with these words, let me begin. So first of all, what are relative Cuntz-Pimsner algebras about? So these are about so you start with the correspondence. So if you haven't heard about correspondence yet, the easiest way to remember is simply the way I think about correspondence is simply you have a linear space and an operator algebra, so a C-star algebra or whatever. And you have some kind of left and right module action. So you have some multiplication that from your operator algebra from left and from right, which does not leave your linear space. And together you have some sort of you have an adjoint space of X. So just a formal adjoint, you could just think okay, put stars everywhere. And if you multiply them together, your linear space with its adjoint, then basically this resembles the inner product. But with values in your operator algebra, in your base coefficient algebra. And but I wouldn't want to think of them as as an inner product, but rather as some sort of abstract additional multiplication between correspondence between your correspondence. And with this way, the question now becomes in what? So this is basically the question about most objects that you start investigating in operator algebras is those generated by some algebraic by some generators and relations, for example a discrete group with relations, or for example say X-Lacker algebras, graph algebras, or inverse semi-group algebras, cross-sectional algebras of Fell bundles. Semi-group algebras for number theory, and also their different quotients with different additional relations. And that's the way that I would like to think about this. So the question is how can you embed so your pair of correspondence, your linear space X and your operator algebra A, into some ambient operator algebra, in which various ways, so in which different operator algebras B's can you embed those or represent those, and in a compatible way, of course, so that the multiplication that I have outlined above, like for example, x star x, becomes actually realized as a concrete, like multiplication between the concrete adjoint of your element x in your ambient operator algebra B together with some y. So like this formal adjoint should become really the adjoint, the involution inside B. And the inner product should really become like then simply this product. But the question is like various realizations. What kind of various realizations can you find in ambient operator algebra such a way? Like how much different can you embed such a correspondence? And which ones can you find, and how many of such exist? Do you maybe find sufficiently many? Like, so for instance, can you always embed your pair compatibly in a faithful way into an ambient operator algebra, or does it always like necessarily introduce some algebraic relations which cancel out some, which forces your representation to have some kernel? And moreover, like, can we classify them? So that's a high stake goal. I mean, like, so it's kind of like a for first attempt, it's like maybe like too much asked for, and usually it's something that it's maybe too hard to expect, at least for on first glance. So for instance, if you talk about discrete groups, there's simply too many of those. Yeah.
I have a question. So usually people ask one question more about the existence of the universal object such B containing this. Yeah, that's or generated by this triple.
Yeah, that's So that is like rather like the, how to say, question zero.
Yes.
And that is usually like answered positively, yes. And that's also the case in here. So you have a universal algebra, but the problem is like not really tractable. It's good for investigating, further investigating the space of representations, the space of ideals, and so on in your quotient. So it exists for this. It's not too hard to verify. Simply like the inner product already like forces your representations to be uniformly bounded.
I have a question about what you wrote in blue.
Yeah.
It is about ideal structure of what?
Yes. So
of A, or
no?
In this universal object? Or?
No. So the question is then, like, if you can classify all such representations, and then imagine imagine then like you pick out one such representation, and then you would like to understand its ideal structure in the ideal structure of this particular representation. So not of A, but like of the ambient operator algebra. And so if you know, like, if you have a parametrization of the entire lattice of so we will talk about equivalent representations. But like for now, like, let's say, like, if you know the entire lattice of representations, then you basically also know the ideal structure for every representation. So of course we ask for that B is generated as an operator algebra by the pieces like X, A, and X star. So like if you multiply things together, so this would be like concatenation of X, 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 or X, A, X, A, A, X, B, X, something like this. Okay, did that answer your question? Like,
yes.
Okay, thanks also for the question. Okay, so one way to go about this is like, so to ask yourself kind of like two questions. The questions are basically like, what kind of algebraic relations does a representation introduce? And So as a first step, that what I realized like was that okay, that's something like rather like trivial, but I'm like it's anyway like it would be important to mention like as for our parameterization at least. Can we maybe classify kernel and co-kernel morphisms in the category of in the category of correspondences? So if you ask more generally, like not just like representations of your correspondence into an ambient operator algebra, but like if you ask for some kind of like morphism between correspondences, like in a compatible way. And the thing is that yes, you can. And so this is like something like some neat trick that if you want to know if you, so basically you pick out some representation and then like you ask yourself what can be the kernel of this representation, some morphism, and then you can ask yourself, okay, what is the kernel of this morphism as a morphism itself? And then you realize that, okay, like such a kernel morphism is of this form, like xk comma k goes to x comma a, where k is, for instance, the kernel of the algebraic morphism from A to B, where YB is another correspondence, and you have, for instance, you have like XA goes to YB. And indeed, it turns out that that any such kernel morphism is of this form. And also, like now, if you want to ask, so even like so further, also like every kernel morphism. So in this way, you can also verify that every kernel morphism exists. And furthermore, like that so when you now want to understand like what kind of co-kernel morphisms exist and how do they look like, then basically you do some neat trick. You say, okay, yeah, I don't want to go into the details for this, but basically like you will find that like every co-kernel morphism is furthermore also basically of this form, namely instead of xk comma k goes to x comma a, but instead x comma a goes to x mod xk a mod k. And for some k. But you can't just like choose any k. So such a k must be, of course, a kernel of some morphism. And this also brings some additional relation, which which I'll talk about on the.
Sorry, Alex.
Yes.
So what do you mean by a co-kernel morphism?
So it's the so this one here. This would be the co-kernel of this morphism here. Goes to, in this case, it would be something like that. Then you ask yourself, what is this? Such that this composition here is 0, and it's like the optimal solution for this. So it's basically like the core of kernel, and kernel would be like so in this case, we can actually write this. Okay. This is the optimal solution for when do you have something like this is 0. With this k here given by this.
Do you mean that these pairs form an exact category?
I think for an exact category, you need some more structure. For instance, like the category is not additive.
So this category is not additive.
Yes, this category is not additive because basically you have the morphism that goes.
It contains this ring part.
Yeah. But you can define like kernel and co-kernel morphisms like as if like you didn't know what is an additive category. That's like optimal solution for something like making it 0. I don't know the word right now. Okay, did that answer, Mariusz? Okay. So let me.
So this means you are considering these kernels and co-kernels in the ambient category of vector spaces, pairs of vector spaces.
No. You don't need to.
Models.
You don't need an additive category to define what is a kernel morphism or what is a co-kernel morphism. The only thing you need to know.
Okay, so
in
at
order
least
to
you
define,
must have sets with distinguished element.
you don't even need that. You just need a zero morphism. You need like you need a consistent system of zero morphism. So something like this, like you need something like 0, phi is 0, and also phi is 0. That's sufficient. So you don't need to know what is like sum of morphisms. That's just a product here. Right? Okay. But the nice thing is, like, how to say, you can reduce now like the general case like of some general morphism into like you can cut it into pieces. Like one is the co-kernel, and the other part turns out to be a faithful embedding of correspondences in the sense that this one simply lies inside this and this lies inside here, and then like everything matches. Okay. Now also let me define what is a general morphism here. A general morphism, like because I haven't specified it yet, but it will become now relevant. So general morphism between correspondences is simply like that matches up, like that does the like the left and right left multiplication is compatible, right multiplication is compatible, and the inner product is compatible. And so this would be saying something like this. This one here is a compatible, so the map, how to say, you get an induced map, and for example, this induced map, so simply this one here is compatible with this one here. Or for example, like this one here is of course a subspace of X. Oh. This is a subspace of X, and this is a subspace of Y. So you can treat this, for example, like this part here, but this agrees also with the, how you say, taking the product like this.
Alex, can I
yeah,
just ask
yeah.
a question about notation? So when you write X star times X is a, so when you have X is a linear space, X star is the sort of a dual space, in some sense, and that there is a pairing between X and X star valued in A, right? So that's what you mean by
yes.
X star times X.
But you can also define, like for example, you can also define a map tau that goes from, like in a very silly way, it goes from X star X to Y star Y as a just formal tensor product, for instance.
Okay.
And then you can just say, okay, like tau of X star tensor Y is just defined like how you would define it. Like, but this is like also like matches up. So the thing is that because you can identify like this formal tensor product in some way, so it's not precisely, but I mean, like, in some way, like it should resemble like the inner product like that you obtain on your correspondence. Like this kind of like morphism that you obtain here should match up like with this morphism that you had on the base coefficient algebra. So you could say, like, for example, this one here, of course, a subspace of A, and this is a subspace of B. And then so you have two different ways of like going from left to right, and that these are compatible. And the same way like here also, and here and here.
So they do not follow from the previous conditions.
This follows. This is basically how to say incorporated in here.
Oh.
This one here is incorporated here. Sorry, this one here, this one over here. And here there is no compatibility condition, right? That's just like some free tensor product, formal tensor product. But now here's an issue. Namely, you can here formally define like your map, like tau. And then there's also another map sometimes, and namely phi. Let me get to this now. This is the next slide. So, so the next question arising is like, so what kind of additional algebraic relations, like asides like having considering co-kernel factorization, and there is like an issue. So or not an issue. I'm like, it's like some interesting piece. So you can have an element in A, which acts on X as a compact operator. So there exists some K in X star X in XX star as a compact operator. And this is like quotation marks here. It's the meaning that A acts as like some compact operator. So that more precisely written out, this would be like A minus K acting on X. They agree. They agree as like operators on X. Now, if you have such an element, then you can follow it then you can follow two different ways. Right? Like you can start from here, from your base coefficient algebra, with your phi, go to here. And then, so this is one here is like, this is not precise. This is like, actually like you consider this into L of Y, like as operators, like from the left, by left action. But then you could also follow instead, like going first here, like if you have an element in here, on this one here, and then follow with your tau. And the question is, how much do those agree? And how to say, written out algebraically, it's maybe like this is the way like you would check things, because this is just like how to say motivate like why like some compatibility comes up. It's like this would be like so this would be like the Pell bundle perspective, but the algebraic perspective is like how to say what kind of algebraic relations you obtain additionally, and this would be something like this. If suppose you have some A in here, so which agrees with some compact operator as acting on X, then what about this one here? Will those also agree when you follow them? And that's not always the case. So we can define the amount of covariance as, for this one here, as an ideal inside A, which is simply like the difference. So basically, how much they agree. So when everything that is in the kernel of this is basically telling you everything that where this diagram here commutes. And this gives you like an additional, measure of your representation, which is like an algebraic relation additionally. Now the thing is like when we looked at this picture here, we could first follow this step here, like make it go to the co-kernel and then obtain like a faithful embedding of the correspondence. And then for faithful correspondences, like if you have a faithful correspondence, like in some ambient operator algebra for simplicity, then there's an observation by Katsura which tells you that like the covariance is actually can never be it usually cannot be, is actually usually strictly below. So it's always orthogonal to the complement to the orthogonal always orthogonal to the kernel of the left action on X, which is which also like how to say cannot be always like the whole thing here. So basically you have like an upper bound, namely you have this thing here. There's a maximal possible covariance that some faithful representation can have. So, and the maximal one that you could possibly have is exactly the orthogonal complement of the kernel of the left action within this space that you can achieve. So it's not that it can always like the maximal possible one. It's not always possible that you can achieve like all of these that this one here commutes on, this diagram commutes on all of those ones. But there's an upper bound, and the upper bound is dictated by your left action as an intrinsic obstruction. So when we look for covariances like this, they cannot go all the way up to this ideal, but they're always bounded by this.
Sorry, could you come back to this
Yeah.
kernel of the action of A on X? What do you mean by this?
So kernel of the left action of the operator algebra on X is an ideal. It's a two-sided closed ideal inside A. So inside here. And if you take the orthogonal complement, so there's like you can take a two-sided or like
Yes, but what is this kernel of the action of A on X?
Mhm.
What is this? Is it an annihilator? What is this?
Yeah, annihilator.
Classical terms.
Annihilator. Let's maybe go through an example. So let's see what kind of case we can have and what kind of covariances we can have. Okay, so what I figured out is like that there's so these pieces were kind of like known. So this one here was known and this one here was known. So okay, so this one was known. And the thing is like that this gives you an intrinsic characterization of what can be a kernel, like a K for a kernel. And these are only those ones here which satisfy this kind of relation here. And we also figured out now like there is this obstruction by Katsura, namely this one here, that they must be always orthogonal to the kernel. So this gives you like this kind of like upper bound here. So this you can view like this is some discrete condition, a discrete obstruction, and this as some upper bound.
What's the orthogonal complement means like this?
Mm-hmm. Something like this. A I believe one side was enough, but you can also ask for both. There was some trick about it because it's two-sided.
Mm-hmm. Thanks.
Okay, thanks for the question. Okay, let's maybe go through an example. So the correspondence, for example, the easiest way that at least that I remember those is those coming from graph algebras, and we are like on a graph algebra workshop, so operator algebras is one can see. So let's start with an example of the graph algebra. And so one example would be like you take, for example, this graph. So I picked this out like to give you something non-trivial. So you have some vertices A and B, and you have two edges X and W. And so this, the vertices, they define your operator algebra, like as you would think of usually. And the edges X and W define your linear space. And now we need to know like what are the multiplication rules between X and A and between X star and X. So for example, if you take X star with X itself, it should be something like the source partial isometry. So this should be A. And similarly for W, so W star W should be the source partial, the source projection of your partial isometry, which should be your projection B. Yeah. Yay. No. Yeah, it's not the triplet. If you take the absolute Cuntz-Pimsner, it will be the triplet, but we'll get to that. Okay, and then what you do is like you multiply. So for example, now you can imagine, right? I'm like, if you take some X and you multiply it by A from the right-hand side, it will be like saying like, okay, A is anyway already like your source projection of your X, so they should be an identity from the right. And from the left, you should have now like the range of X should be below the projection B. So this would be this one here. And similarly for W. So W, if you take W and you multiply it from the right with B, that's exactly like source projection. So this should be like WB should be W. And from the left, if you multiply B from the left on W, then B should be a projection then the range projection of W should be below B. So B is an identity from the left on W. And then now kernel ideas for this. So I wrote this here quickly, but the easier way to remember in these cases for graph algebra is that this condition here that I didn't explain. So this is called an invariant idea. Is actually equivalent to this condition here. That means that it's a hereditary idea. And the meaning is that if you take some kernel, or so K inside an idea inside A, so this thing up here, some idea in here. So this, so I just wrote it just in terms of the vertices, that it encapsulates. So for example, K could be no vertices, so K would be just 0, and then trivially this is satisfied. K could be just the complex numbers times this vertex A here. And then so the thing is now, if you multiply, so we need to check that this condition here is satisfied. So we can simply do this one quickly. So for example, A times X, which morphisms do we have in here? Sorry, which edges do we have in here? So for example, A times W is 0, but we only get A times X. Sorry, there's nothing, right? Whereas on the other hand, if we consider XA, then there's only the X. So this is contained in here. So this is an hereditary vertex. But if we now consider, for instance, we consider instead, for example, K to be this thing here, then the condition that we are asking for here, that it should be hereditary, is Kx, which is now B times the vertices, the edges that we have. So B, for example, times X. I'm just going to write like this now, union of just edges. B on X is just EX, but B on W is 0. So let's just take it. So this will be just this one here. Whereas on the other hand, so this is whereas on the other hand, XK is now X union W times B. And here we get not just yeah, I think I wanted to have this not hereditary. So X times B is 0. So we only obtain BW, and these are this is not contained. So this is not hereditary idea. Okay. And then similarly, you can check something like this. So basically what you do is you check if it's a hereditary idea. Now for the covariance, we need to, so let's look at the definition here. The maximal covariance is this thing here. It's the kernel, is the orthogonal complement of the kernel of the left action. For a graph, this would be simply how to say, which vertex, so the kernel is which vertices act trivially on the edge set. So basically, they are not the range of any vertex. And then the orthogonal complement. So this would be simply the sources. And on the other hand, now, so this basically asking for the orthogonal complement would be simply asking for vertices that are not sources. And on the other hand, XX, so those that act as compact operators on the edge set would be simply that there's only finitely many edges going into your vertex. So this would be this would be not your infinite receivers. And so if you plug them together, you get the ones that are not infinite receivers and not sources. So these are exactly the regular vertices. So this is exactly the regular vertices. And so any kind of ideal between all the regular vertices and between no vertices and all the regular vertices can come up in principle as a covariance ideal. And so this is something that one can check out here. For example, this one here is not bounded by this one here, because here we have that the only regular vertices are 3. So only those 2. Okay. Now the whole part now is that these 2 ideals are already sufficient to classify and to parameterize all gauge equivalent representations of a correspondence. So these 2 abstractions are all that you can possibly find in nature if you consider gauge equivalent representation. So if you want to know what is a gauge equivalent representation, the only thing you need to know is what is its kernel and what is the covariance if you could pass to the co-kernel. So these 2 are your invariants that are classified. And even like if you just pick out any kind of like kernel invariant ideal as an invariant ideal, and any kind of covariance ideal as bounded from above by the possible maximum one, then also you can find such a gauge equivalent representation which has exactly this kernel and exactly this covariance. So these really tell you the entire lattice of gauge equivalent representations. So basically now the entire parameterization of your gauge equivalent lattice, of your lattice of gauge equivalent representations, is exactly you consider all the co-kernel morphisms starting from your original correspondence x. So for example, x goes to x mod k, or x goes to x mod l, and then for example you can consider x goes to x mod k plus l, all the way to, for example, the zero correspondence. So you first do this step, you pass to the co-kernel, and then from the co-kernel, so pick out one. So for instance, I don't know, this one here, that would be, and then you consider all the possible covariances below the maximal one for this quotient correspondence. And so you can have, for example, the 0, 1, j being 0. But this would be or like, yeah, so I and j, you can have j not being 0, you can have some other covariance all the way to the possible maximum one. And each of those defines exactly one gauge equivalent representations, and each of them lies exactly somewhere here. So you first, so each gauge equivalent representation says you go somewhere here. And then from here, you choose like some path, like say some path like this. Okay. So I'm not going to delve now into this, how you prove this, but basically what you do is like the general version of the gauge theorem tells you that, okay, if you take some generic some gauge equivalent representation, and you consider its own kernel and its own covariance, then this is exactly like the relative Cuntz-Pimsner algebra for this. So like the universal one with these kind of like relations here. So every gauge equivalent representation arises in such a way. So there's a gauge action that you can define. So you can define it you can define an abstract gauge action on your correspondence, like kind of like that. So like your elements in your linear space X, they become, for example, if you have an element on a torus, you multiply it by this space, e to the I pi, for example, on your X.
Any correspondence, then no. This gauge group acts on all the correspondence. Or?
Yeah, so the gauge group acts on your linear space X simply by multiplication by the space of your torus, and on the base coefficient algebra on A, it acts trivially. So just by multiplying by 1. It doesn't like the trivial action. And then you ask yourself, like, given any kind of, suppose you have a gauge action, so gauge current representation would be like that you have a gauge action also on your ambient algebra in such a way that like that if you embed this one here inside here, maybe like this picture would be best for this, that here you have a gauge action also, such that in this regime, I mean, like, it doesn't need to be like a just multiplication by your phase, right? It can be something obscure, right? But in this kind of area, it multiplies by your simply by your phase. Here it multiplies by the inverse of your phase, and here it multiplies by 0, by 1, like e to the I 0. This would be a gauge action. Does this answer like your question?
This is also means you have a Z grading something
Yes.
on X.
Yes, correct, exactly.
So then it's an actual assumption that you're gonna assume.
Yes. We're only going to talk about gauge equivalent representation. Yeah. So representations where the target operator alpha has a gauge comes not just admit, comes with a specified gauge action. Yeah.
So then you just shrink your category of correspondence. You're gonna specialize for those.
Yes.
Okay.
Yeah. Okay, but then the question could be still that, okay, you can realize every representation by some kernel covariance pair, like by some pair of ideas. But it could be still that there could be like some other k prime and j prime that also does the same, that realizes the same b. So this would be like how to say that well, you can like they exhaust all the representations, but I mean like you can have some that simply like you could have that something like this, like O of k is equal to O of k, like as a representation, equal to O of k prime j prime. You could have this in principle, but it turns out that you don't have it. So in effect, these kernel covariance pairs are also parameterizing in the sense that, like how to say, if you pass to the representation, to the universal such representation for this pair, and you consider its own this kernel, then you retrieve the original ideal k. And the same also for the covariance. So you don't lose.
So could you read again in words the
Yes.
content of this theorem?
Yes. So the first thing tells you that, like how to say, you can reach every gauge equivalent representation as the relative Cuntz-Pimsner algebra for some k and for some kernel covariance pair. So for some invariant ideal k and some bounded ideal j bounded by some maximum by some of the quotient correspondence. So you can find some pair k and j that realizes this gauge equivalent representation. So you kind of like you have the range of this is all gauge equivalent. Sorry?
So this is about surjectivity.
Exactly. And the other one is about injectivity. So that like, yeah. And furthermore, like you can guess that, okay, furthermore, it's also an order isomorphism in the sense that, like how to say, one gauge equivalent representation comes after the other one. So this would be like just shorthand for like how to say this is like one comes after the other one. And then like this is exactly this if and only if these ideas are contained inside. And then because these ideas live on the quotient correspondences, you can also take them back into the original correspondence, and then you can compare them in there, and you can see that, okay, they must be also like I must be contained inside J. So the nice thing is, like now what we can do is we can read off the entire lattice of gauge equivalent representations from the correspondence intrinsically. Let's see some example, maybe this one here. So imagine you take this graph. And now we can read off like all the kernel as all the hereditary ideals. So for instance, we can take, I think I forgot one. This is a hereditary ideal. This is hereditary. No, this right? Okay. This is hereditary ideal. No, this one here isn't hereditary. Yeah, exactly. And then we pass to the quotient correspondence. So this would be quotient graph, or I don't know, like maybe like I shouldn't call it quotient graph. You know, like okay. So So you get this corresponding graph here. And then you can also take, this is also an hereditary idea. So you can mod out also by this vertex set here, you get the empty graph. And then what you do as a next step is you pick out one. So let's say this one here, and then you read off like the regular vertices. So the regular vertices are A and B, so we get all of them, right? So we get J is 0, J is A, J is B, and J is AB. Here I already consider like for this one here, I already consider like the pullback. If you go like down, if you add like the A that we have mod out, and then we have basically this is like the 0 in here, union with the things that we mod out because we want to like compare those. And if you, this is also a regular vertex, so we can also take this for our J. So this would be this one here, together with the A from that we have mod out from here. And now you can simply read off like, so this is already like how to say, inside your base. This is already inside your coefficient algebra, like kind of as pullback ideas inside here. And the last step, of course, something that's also like this one here is just like, okay, there's no vertex to choose. And then we just simply pull back from this quotient into the original algebra A. So we get A union B. And now we can read off like, okay, which one lies in where? So of course, these lie in here. That's not so hard. This lies in here, this lies in here, this lies also in here. And of course, everything lies here. But now, this one here lies in here, but this one here does not lie in here. So we get some interesting ideal structure. This only further lies in here. So that's something that gives you some interesting, like, okay, there is some interesting phenomena happening. So a little bit more. So the lattice structure may be quite interwoven. So for example, you can ask yourself from where, if you imagine you start, you pick out one of those, which ones factor into here. And it could be that, for example, like by some previous co-kernel kernel idea, these ones, for example, could not factor over here anymore, but only this and this one here. It could be also, for example, you could ask like, if you pick out one of those, it could be that it does not go inside here, it does not go inside here, but it only goes inside here and inside here. That's what we had in the previous picture, like this one here. It does not go into here, it only goes starts off here. Or you could have it worse. You could have that it does not go anywhere here. But the next possible kind of pit stop is like somewhere much further. I'm not going to go into this one here, but this basically like this is like a summary of like these pictures here. Basically like everything reformulated in terms of like this condition here. And you can ask yourself like, for example, like something like, okay, you can compute the meet of an arbitrary number of kernel covariance ideas, and you can get some negative examples. Okay, maybe, yeah, so maybe let me like now that we know, so this was like kind of like so far about the lattice, and keep remembering that we have this lattice isomorphism, so we can rephrase everything in terms of like inclusion of kernel covariance ideas. And the thing is now that like this also lets you like, for example, like ask about we can ask now like applications, and the first application of this classification would be like can we classify Pimsner dilation? The Pimsner dilation would be something like this. Imagine you have a relative Cuntz-Pimsner algebra for, so not for the maximal covariance, but for some smaller covariance. Like imagine you have not taken all the Kuntz-Krieger relations, but only some of that, like a partial piece of the Kuntz-Krieger relations. And then the question would be, so this would be this one here. And the question would be with some I and not the maximal one. And the question would be like, can we realize this as an absolute Cuntz-Pimsner algebra? So with the maximal covariance, but by some possible different covariance by some different correspondence between. And so this would be like, of course, we know that this, so I'm not going to go into this one here, but we can basically restrict to something like this must be like to the faithful case, and then like this must lie between XA and OXI, and Y must lie inside the first Fourier subspace, and B must lie inside the fixed point algebra. And then if you want to know, like, for say, you would like to have that this one here. So now it comes a nice trick. How to realize that this one here. So how to realize that this one here is the absolute Cuntz-Pimsner for this one here with the maximal correspondence with the maximal covariance. And the thing is that this is possible. This is so this is only possible if there is no further quotient that goes down here, which for which this one here is an embedding. So where you don't introduce new kernel. Or in other words, it basically tells you that this one here is the absolute Cuntz-Pimsner for this one here, if and only if for any, so here this should be Ki. If for any gauge, if this B here detects every gauge invariant ideal. So this is some nice trick that I learned from Ralph Meyer. You can ask kind of like this question instead. But the thing is, we know all the, so like this would be saying detection of gauge invariant ideals, meaning that suppose there's a gauge invariant ideal inside here. And if it has trivial intersection with the coefficient algebra, then the ideal itself must be 0. This is the detection of detection of gauge invariant ideal property. And we know all the gauge equivalent ideals because we know the entire lattice of gauge equivalent representations. We have found it. So, and these are exactly of this form. For some I prime, which lies between the maximal one and the one that we have in here. So if you want to have something like some detection of gauge invariant ideals, then it must detect all of those things here. Well, there's a natural candidate that detects all of those ones here, because these all lie inside this one here. So we can simply take this one here. So if we take this as our B, and we simply take Y to be simply this one here, the first Fourier subspace, then this detects every gauge invariant ideal, and so we get that this relative Cuntz-Pimsner algebra is realized as an absolute Cuntz-Pimsner algebra for exactly the first and the Fourier subspace and the fixed point algebra as corresponding. Now we can do the same, something similar, but this problem is like this one here is a universal object, kind of like this thing here. Not tractable, not very tractable. And so we'd like to have something more combinatorial. And so for this, back to this old problem, we have something that sits in between, like Y and B. They should be like, how do you say, correspondent. So they should multiply into the corresponding correspondingly. And they should detect all of these things here. So we could simply take, for instance, like simply B to be this thing here. This should be. We could simply take B to be exactly the original coefficient algebra times what it should detect, namely this piece here. And this will detect, of course, this will do exactly the job. But the problem is now, how do we choose Y? So we have to choose Y in such a way that if we multiply it by B from the right-hand side, it has to contain X. And if we multiply by B from the right or from the left, it should again lie inside Y. So we have to simply take X together with XB and together with BX. So you get something, you enlarge your X. So to have like the left and right multiplication landing back inside your correspondence. This one here like disappears. But now you have enlarged your X, and now you have to ask yourself, okay, is B again large enough? So you have to consider all the inner products Y star Y. And you have to possibly like add this to your B. So you may need to enlarge your B again. If you're unlucky, you have to enlarge your B, but then you have enlarged your B, then you have to enlarge your Y again to be a correspondence compatible so that the left and right action land back inside. The worst case, you will never stop. In the lucky case, like in this case here, like this canonical one, we stop already after the first step. And that's exactly this thing here. So this thing here, so sorry, this piece here detects exactly the ideas that we'd like to detect. And this is a correspondence together. And so we obtain that this defines this pair, its absolute Cuntz-Pimsner algebra is exactly the one that we're looking for. And you can also find an intrinsic description of this, namely simply like as multiplication, left, right, and so on. And with some vanishing thing. And the nice thing is that, like, how do you say, this is exactly so this combinatorial dilation is exactly a construction that Katsura initiated in order like to realize to classify gauge equivalent representations. So we figured out that this is actually nothing but the combinatorial dilation. And if you also like, for example, if you want to know like what are the so like I have 5 minutes, right? Like that. Yeah. Okay. So if you want to know, for example, if you take a graph algebra and you do this combinatorial dilation, you get back exactly some, I think it's out splitting out. I maybe I missed some out or in splitting, I don't know, Southern convention or but it's like one of those. So it's exactly this construction that you would find. So for instance, if you take this graph here and you take O of this, sorry, if you take the triplets algebra of this, then this is exactly the Cuntz-Pimsner algebra of this graph. And that's exactly what we usually refer to as the triplets graph. But actually it's the combinatorial dilation of the triplets graph. So this can be actually viewed as the triplets graph. And you know, like this one here, for example, like O of this one here would be the absolute Cuntz-Pimsner algebra, you know, like the circle algebra. So you can say this is so basically this one here is the triplets graph. And then you can ask yourself, okay, is this like also combinatorial? Is this combinatorial dilation? Is it actually like, it is much smaller, right? I'm like, it's much more tractable. It's like some combinatorial object. It can simply like paste like your vertices together and get something nice. You don't have something universal. And it was very small already. But the question is it actually the smallest one? Like the smallest B that you could have that has this property? For graph correspondences, it turns out yes, it is minimal. And one question that was not so clear is that is it the unique one? It could be also that there could be some other minimal dilation. But a little bit so interestingly for dynamical systems, this combinatorial dilation. So if you take like a group action on a space, sorry, like if you take an integer action on a space, then this actually combinatorial dilation is not always minimal. And it turns out that so combinatorial dilation, I call it here Katsura dilation, is minimal if and only if the maximal covariance as a subspace inside your topological space is a discrete subspace. So there's basically no more below. This is the second application. I think I'm going to just tell you something. Aha, maybe like, okay, so if you do it like similarly now for, if you use like, again, this lattice, you can simply read off like pullbacks from the lattice. So, and this is shouldn't be so hard to think about now. If you want to know the pullback of this with this one here, like as kind of something like this. So imagine, so I'm going to draw it like this. AI. LJ. AI. Wedge LJ. And then AI. So this was VLJ and this is wedge LJ. These are exactly the pullbacks of relative constraints. And there is no further such, at least like when you like ask for everything, like the maps to be compatible. So in particular, if you imagine, so this is like the last diagram that I draw. Imagine what if, for example, like imagine you take this, I'm going to just draw one example. This is the one that we had like worked together. Imagine you take this graph here. Yeah, like this, exactly. So say here A, B, A, B, C. This one here has no, the first one has no regular vertices. So Toeplitz algebra equals Cuntz-Pimsner. So T equals O. This one also has no regular vertices. So here also T equals O. This one also has no regular vertices. T equals O. There is nothing to mod out more. But this one has a single regular vertex suddenly, because it's not suddenly an infinite receiver anymore. And it's also, but it still remains like not a source. So here we have T is not equal to O. So if you think about like now in terms of lattice, the lattice of kernel covariance ideas, so we have the pullback is exactly this one here with T. And so that's also similarly like, so because T equals O here everywhere, that's also for O, except for the last one. So if you take now this one here, this is not a pullback. So here we have T equals O, T equals O, T equals O. This is not a pullback, because this one here. So this gives you an example of like why absolute. So you can compute every pullback. You know all the pullbacks of relative Cuntz-Pimsner algebra, and you even find that the pullback of absolute Cuntz-Pimsner, the absolute Cuntz-Pimsner algebra is not always the correct one. It may be simply like a relative. And I think that's all that I would like to say. And so thanks for your attention.
Yes, first I have a comment that don't be fooled that my name appeared. I had nothing to do with it. It's all Alex. So okay, that's his result. He's just a very nice person, because we talked about this one example. So first I had a comment. Can you go back to this first example with this graph? No, just oh, here, or just maybe you stop here, because this graph, just so I know, this graph with the Australian convention, this graph with a loop and something incoming to it. Graph C-star algebra of this guy is the Toeplitz algebra, right? With the, okay, because because you stopped me, you said no, and then I got confused. I had to consult Rayburn's book, and okay, there's so and now I have a question about this dilation. Is this dilation anyhow related with what Piotr was talking about several times, that every relative Toeplitz graph C-star algebra is a graph C-star algebra for a different graph, right? So is that connected to this? Okay.
That's exactly.
Okay, thank you.
That's exactly that outsplitting. I think Søren knows this maybe better. By the way, I didn't see it because the videos were okay.
Yes. So what is Cuntz-Pimsner algebras, like in a elementary way? So I do, because I have no ideas, not experts in this. So what is the classical, like generators and representations for Cuntz-Pimsner algebras?
Yeah, so the classical one would be certainly like from starting from Kuntz-Krieger algebra or graph algebra would be more suitable in this context. It would be simply like, how to say, you take a graph, and so then you can consider, like, imagine you didn't take a kernel, but just like some covariance. This would be simply like saying that how many of the vertices would you like to include for your Cuntz-Krieger relation. So you have this kind of like, maybe I can write this down. Let's see, here's some space. So you have this kind of relation that sum over x star equal to a. Sorry, a is equal to this one here for every whenever for the range of x is equal to 3. So basically, you take something like this, and imagine you have all sorts of edges going into A here, and then you sum them all up. So that would be simply like the range projection. So this would be something like this one here. Imagine this is your A, and then you imagine you have like this here. This is x star, this is y star, and this is okay. So this would be like A is here, and then how do you say, x goes into A, and y goes into A, and w goes into A, and z goes into A.
Yes, you wrote C on.
Oh, that was, I'm a little bit like, how to say, I have some troubles, I think, with the writing. Okay. No. Yes. Like this. So you ask yourself, in which vertices would you like to have that? These ones here. In which of the vertices would you like to have the range projection of the edges fill up your vertex? So you could also ask. You could also not ask for every vertex to be filled up by its range projection.
So the title, actually, you meant like Cuntz-Pimsner correspondence. It will be more because you're talking about a correspondence, like in.
So it's called Cuntz-Pimsner algebras because it started off like from Cuntz algebra,
Yeah,
and Cuntz-Krieger algebra, then graph algebra, and then Pimsner got involved and introduced like Cuntz-Pimsner algebra as a generalization for correspondences, because you can always look at the graph as a correspondence also.
So the result you're talking about is more general than graph correspondence, or mainly for correspondence?
Yes, it's more general. So it's for correspondence.
Okay.
So the class of correspondence is a little bit larger, more complicated. It contains, for instance, reactions on topological spaces, where your coefficient algebra A would be C0x, and x would be apricot. You can turn them into file bundles, and that's where they're.
Thanks.
Other questions? So let me see online.
I think Søren has a question.
Yes, Søren, please.
Yes, so this is becoming sort of a meta question for this whole conference, but so I sort of know, I think, what happens when you try to do this equivariantly, and you discussed this already, but how about the diagonal? Have you thought about this at some point? I don't remember.
The diagonal would be like something like the diagonal is not just a fixed point algebra, right? Like,
no, it's contained in the fixed point algebra, and it's commutative. I don't know if it makes sense for a general Cuntz-Pimsner.
In terms of,
but I think that some of the basic examples of this pullback construction, it's actually possible to do it preserving the diagonal. So I guess that would be very interesting if this is something that could be done. more generally.
Yes, I think so. Some questions, you know, like for instance, like gauge action is something that matches up nicely with like correspondence, with the picture of correspondences. On the other hand, if you think about some other questions, like I think the diagonal comes up naturally in the group point picture.
That is true. That is true.
Yes.
So maybe this model doesn't work so well for that. But I
Exactly.
think also for the equivariance, I mean, it's it has to do with the length of the paths. And
Exactly.
Piotr explained also in his talk that this is not something you always get, right? So this
Yes.
is that's natural. That
Exactly. Yeah. Exactly. I don't know. Do you know the Drinnen-Tromford Morita equivalence? Is it like does it preserve somewhat like diagonal?
I would expect it did, yes.
Yes.
But
Because then this would
I
be something.
don't know that for a fact, but I think it should.
Because
I see what you're saying.
because the Drinnen-Tromford Morita equivalence is something that does not act between like the correspondence and like some other correspondence, but rather it's like, how to say, involving like longer paths.
Yeah.
And that would be like something that goes like beyond like goes more about the between the file bundles, for example.
Right.
Correspondence.
Yes.
Yeah. But then you can have this Drinnen-Tromford that does not even like match up with the file bundles. Like if you have some infinite arbitrary long things. Yes.
I'd like to make a follow-up question to Soren's, just because you
Oh, yeah.
reminded me that you have a graph algebra for this. As you said in your talk, that gauge action comes from spinning all of the generating partial isometries of edges by the same complex number z. Now, if you apply a different z to every edge independently, of course you have this huge compact abelian group, but still, that's how you would pick out as the fixed point algebra the diagonal in this case. So could there be some sort of analog in the more general context of functional algebra?
Yeah, so the thing is like really like these kind of questions also, like for example, like if you take like you know, like you have this example with the what is it, a loop, and you know that this is Morita equivalent to like, I mean like with like n edges, you know, like this is a Morita equivalent to mn, I mean like it's mn tensor ct, and you know this one here is Morita equivalent to ct, right? Like, but in a non-occurrent way. Yeah, and also like it's simply like, yeah, I don't know, like I'm like between. So can you say it again, like your suggestion?
It's a sort of a naive idea. Is you let one copy, you know, you have a big product of copies of the circle, one copy for each edge, and so given an edge tuple of elements of the circle, you could spin each each partial isometry for an edge by its own complex phase.
Yes.
And then you get a much smaller fixed point algebra, which would be exactly the diagonal. It would be, you'd have to have S mu star or mu or equal in order to be.
Yes, it's this construction with the like how to say kind of like crossing it by z, right? Like I think there's this one construction like that does this.
It's a silly question because it's so specific to the situation of a graph algebra, but it shows where the diagonal might come from.
Yeah. Yeah.
I don't know whether it is even conceivable that this idea could be made more general.
I think so, because I mean
it's also, if I may, it's also probably related to this weighted gauge action that Kevin mentioned in his talk, which was introduced by Matsumoto. I'm sure this is not as precise as what you're suggesting, Jack, but it's probably somewhere halfway.
Yeah.
But I think this is also a very interesting object that we haven't really understood yet.
Yeah. And then there's even like, how to say, if you make it tensor k, right? I mean, like then there was this thing with like, if you tensor and compact operators that you can realize it's also like as a graph algebra, but within kind of like the non-canonical gauge action, which acts like trivially on the compact operators. Like that was also something like weird, right? Like, yeah. So
I also like to add a comment on this question when we're sorting that if you, I think it's a very hard question because if you take a statistical correspondence over a commutative system algebra, it's not always known if this has a group point model. So what would be the diagonal if you don't have a group point model? Is kind of a hard question to answer, I guess.
so this would be like that you take a fell bundle, which is something like not saturated or something like that.
Not even that, I think, because in the correspondence, you can have some kind of inner product that is related to an integral instead of being just a sum. And then you have something like that. Yeah, how do you build a group out of that? Is kind of, even if you have the hard measures, it's still kind of hard to do this. I have a few examples that I'm trying to do for a long time and I still don't know how to do it. If you have a statistical correspondence of a commutative system algebra, how do you do this group point algebra? So I would guess that if you only look at the statistical correspondence and trying to find some kind of diagonal is going to be a hard problem to do as well.
Yeah, I can imagine. Yeah.
Okay, so any more questions? And if not, we can thank the speaker again. And I will stop recording.